Hello. 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 Hello.
Beer, wine. Yes, always. Spatially resolved clues about giant planets with JWST. Yeah, thank you.
Once he uses full voice, we heard it.
All right, let's get started. Come on in, take a seat. So welcome to our first colloquium of the spring term. So it's my great pleasure to introduce the speaker to kick off our spring colloquium session. Dr. Laurent Pueyo, coming from Space Telescope Science Institute. I've known Laurent for a very long time. Laurent got his PhD from Princeton back in 2008, and then came to JPL as a NASA postdoc. And then he got his Sagan Fellowship and took it back east to Johns Hopkins University and Space Telescope. He became an astronomer at Space Telescope in 2013 and has been there since then. So Laurent was really instrumental in JWST's success in the direct imaging and spectroscopy of exoplanets, but he's also been an amazing innovator in wavefront sensing and control, coronagraphy, mission design. So he participated in multiple mission design studies. He was also and is still involved in the Roman coronagraph and the Habitable World Observatory. So let's give Laurent a warm welcome to Caltech, and he will tell us a lot about the latest results from James Webb in direct imaging of exoplanets.
Thank you, Dimitri. Thank you, everyone, for being here. It's a great pleasure to be back on campus after over almost 2 decades. It's been a long time. So I'm going to tell you about giant exoplanets with JWST. So let's get into it. Some fun facts about giant exoplanets. The ratio of small exoplanets to giant exoplanets known today is about 3:1. If you correct for completeness, it's 5 to 10:1, depending on how you correct for completeness. The closest giant planet to Earth is 365 million miles away. The closest rocky planet is Mars. It's 54 million miles away. We do not live on the surface of a giant exoplanet. We do not live on the moon of a giant exoplanet. And we've never sent a rover on a giant exoplanet. My point here is that I'm a father of 3, and giant exoplanets, they're the middle child of exoplanets. We don't care so much about them. And I'm going to spend the next hour or so telling you why we should think a little more about giant exoplanets and what we can do with these objects with JWST. Now, one of the nice things you can do about the giant planets in our solar system is send probes like Juno there. And Juno has completely changed our thinking about Jupiter, about the interior of Jupiter, and this idea of having a dilute core in the interior of Jupiter, as opposed to the previous picture, which was a solid core in just a big gaseous envelope. The leading hypothesis to explain this dilute core, it's mostly in this phase here, where you first form the core, then you have runaway gas accretion, and then in between, if you tune the ratio of gas to solids accreted, you can sort of explain this dilute core. Another more catastrophic explanation would be giant impacts that kind of stir up the interior of Jupiter. It's hard to explain how giant impacts would form a dilute core in Jupiter and Saturn, so this hypothesis is not very favored now, but we can't really tell based on the data. The unfortunate thing is that we only have 4 giant planets in our solar system, and the gist of my talk is we're not going to get into the deep interior of giant exoplanets, but try to assemble a bigger sample from an astrophysical standpoint, looking at exoplanets, and try to get to important questions about the formation and evolution of a giant planet. All right, so more fun facts. Well, in our solar system, the ratio is 4:4, giant to small planets. The longest period probed by radial velocity is 30 years. And the period of the 3-hour giant planets in our solar system is above 30 years. It's not to say you can do amazing things with data like the California Planet Search data on giant planets. You can correct for completeness. You can do amazing work. But radial velocity is a waiting game. And if you have something that's a 50 or 60 years period, you have to wait 50 or 60 years to really to get close orbits. And this is one of the disadvantages of what I call time result detection of exoplanets. When you see an exoplanet talk, everybody goes through the different techniques. I think at this point, 2 techniques are emerging: time result, spatial result. time resolved is the photons of the planet and the photons of the star land on the same pixel, and using temporal modulation to discriminate them. It could be radial velocity, sorry. Oops, I missed it. It could be radial velocity, it could be transit, it could be gravitational microlensing, using the time domain, and you're sensitive to different orbital parameter space based on those time constants. What I'm going to talk to you about today is spatially resolving them. So when we think about spatially resolving them, we think about these, we call it the direct imaging technique, which you have this beautiful image here obtained with Keck of the 4 planets orbiting the HRE 79 star. But at this point, the community is starting really to move away from taking these images. Once you know where a planet is, you don't need to see to get a full image of the full system. You can just put the planet on the spectrograph. This is what Dimitri has been doing with Keck. Or you could put the planet on a fiber here and push it through an interferometer. This is the gravity VLTI interferometer in Chile. But all these techniques, they have a common thread, is we're resolving spatially the photons on the star and the planet. And this is going to be what I'm going to be telling you today. And that's the movie of the HRE 79 planets orbiting their star. So let's place things in context. I'm going to be jumping around between planets and brown dwarf and temperature. So let's set the stage here and then slow me down if I go a little too fast later on in my talk. So what you're looking at here is the emergence spectrum of M star, 2 brown dwarfs, and Jupiter here. So you go from about 3,000 K to 100 K. As you just follow the black body, those hotter objects, so the brown dwarfs, they're really the place to see them is the near infrared 1 to 2 microns, and you can do that with Keck and VLT. All the way to K-band, you can do the observations, and you can take advantage of the 8 to 10 meter resolution of those big telescopes. As you get cooler in temperature, you can see that most of the energy emitted by the planet is starting to go past 3 or 4 microns. And that's where ground-based telescopes are struggling because you're fighting with the Earth background. And with JWST, you go to space, you have a cool telescope. So, I mean, this is the same story as Spitzer. And you're more sensitive to these much cooler objects here. And then you go all the way down to Jupiter, where you can't even, it's really hard to do with something like JWST NIRSpec, I mean, if it's an exoplanet, because most of the energy is emitted past like 7, or it's about at 10 microns. And then you have to use a JWST MIRI instrument. Most of my talk is going to be at these wavelengths here, because that's where I did all my work over the past 4 or 5 years. But we're starting to see very interesting emergent trends with the JWST MIRI instrument. The other point about this plot is I'm going to be switching between planets and brown dwarfs. We're looking at the emergent spectrum of light bulbs, very cool light bulbs. It could be a cool brown dwarf that has a high mass. It could be a low mass planet, but that's still forming. That's still that's still emitting light from the formation process. And they're both at the same temperature. And they have distinct spectral signature and signature in the atmospheres I'm going to go over. But I'm going to be switching from one to another throughout this talk. All right, so here's what I'm going to be talking about. I'm going to be talking about reconnaissance of giant exoplanet system, their architecture, and then the deep dive we can do once we get spectroscopy with the systems. So the reconnaissance is something actually we started a long time ago. It's just doing blind surveys. You take a big sample of young stars, and you're looking for giant planets that still have some deformation energy around those stars. And you're trying to say something about how planet forms and do some demographics. So this is circa 2005, 2020. This is how I actually got started in this field, working with people in the room on a survey at Palomar, trying to do this. The punchline here is we didn't find that many planets. It was kind of a downer. These are like, a few objects here. This is the completeness of the sensitivity of the survey. And these are the things we detected. Hundreds of ground-based telescope time were invested, and we didn't find much. We didn't find much material to do nice demographics. So what happened here? Well, the main conclusion is the giant planets grow easier around massive stars. That's been established by these surveys. the bulk of the giant planet semi-major axis distribution, it peaks a little too close to the star. And even with the 8-meter telescope and the modern coronagraph and the modern theoretic system, it's really hard to see the bulk of this population. And so we're sensitive to sort of like the tail of the semi-major axis distribution. This is something that's, we kind of hinted at, we sort of knew about it as we were going through these surveys. And then in 2019, the California Planet Search team published this beautiful paper really showing that based on the RV data, the planet distribution has this bell shape here and peaks between 3 to 5 AU. These surveys, these ground-based surveys, are more sensitive past like 10, 20 AU. So we were just not probing the right part of the astrophysical parameter space. This could be changed with a 40-meter telescope, but with the 8 to 10-meter telescope, that's the best you can do. And this picture is actually pretty consistent when you take the best fit model from this paper and push it through something like the GPI survey. There's something that's missing here, though. This is pretty true all the way down to, say, 1 to 2 Jupiter masses. If you go to sub-Jupiter, closer to Saturn, it's at long periods, radial velocity is struggling a little bit. We need to wait for more time. And those surveys are completely blind to those. With Webb, you're going to lower masses for young age. So you're going lower in temperature. So that's where things start peaking at 3 or 4 microns. And you are very sensitive to objects that go down to all the way to 0.2 Jupiter masses. There's been a massive investment of wet time over the first 2 or 3 cycles, mostly led by Aaron Carter and Beth Biller, trying to do blind surveys and try to find Saturn analogs in orbits between, starting at 20 AU all the way out, and try to identify those. These are 4 candidates here. This is the kind of figures we use to discriminate our candidates from either background star in our galaxy or tiny red dots and electroelectric sources. And you can see here there is, a bunch of candidates here that can't really be explained by those 2 populations. There are outliers, so we need to do follow-ups. For cycle 5, a follow-up program was just approved to really try to confirm if all of these, I think there is like 30 of them, sub-Jupiter candidates are actually sub-Jupiters or if they're background stars. So we'll get the answer within probably a year or 2 here. Now, that was for the younger stars, so sub-Jupiters. Now, how about the older stars? What can we do with old stars, old field stars, or more nearby? We can't really do surveys. There are just too many of them. But what we can do is what I call prior informed surveys or prior informed observations. So in this is something that has emerged over the past 5 years, but this very nice figure from William Thompson that he published a couple of months ago. So you have time here. You have astrometric position of the star with respect to the field. And if there's a planet around the star, it makes the centroid of the star wobble. You can look at the proper motion vector from Hipparchus. You can look at proper motion vector from Gaia, the difference between Gaia DR2 or DR3. You can add radial velocity if you have data on the star. And with this long baseline and all this data, you can sort of predict, well, this star is just moving a little too much, and there must be a planet over there. And this is exactly what Elizabeth Matthew did with JWST MIRI, just doing MIRI coronagraph observations of Epsilon DAB. And sure enough, there is a 300 Kelvin object here orbiting this planet. What's really nice is this object is, I think, within like less than 10 parsecs. It's very nearby. You have lots of photons. You can go back and do detailed spectroscopy of this object. And the program actually, I think, Jerry Swan was here at Caltech, is leading those observations, and there's going to be a lot of interesting results that are going to come out. Here is another example here. This one I'm pretty proud of. These are the predictions for the position of this planet based on Gaia, Hipparchus, and there was Hubble FGS data. And this is where we found the point source. So the point source is right here. It's right here in these images. At this point, we decided with Daniela to publish the paper without a second epoch. Just the likelihood of having a galaxy landing exactly where all the indirect measurements are predicting is becoming very, very low. The likelihood of having a galaxy in the field is not low. We actually have a galaxy in the field. So and of course, at this point, we've proposed two more times to confirm, to get a second epoch, to really confirm that this source is physically associated. The answer from the TAC has been, now we're sure it's a planet, and they rejected our proposals. So, but this is the kind of things once you have prior informed surveys. Now, as part of reconnaissance, when you get those images, the next thing you can do without doing spectroscopy is to get colors. And this is the HRD 79 system looked with 3 narrow filters, medium band filters, sorry, with JWST NIRSpec. And the planets have different colors. It's a pretty image we made for an NASA press release here. And really, all the work getting this precision photometry was done by Jens Kammerer and William Balmer, who are in our group. The interesting figure from this paper is this color diagram here. This is all the non-brown dwarfs observed these wavelengths, some of them with a carrier, some of them with JWST. Some of them are spectroscopic data, and we just propagated those spectra through a photometric filter. And this is what we're finding for the HRS planets. They look like they're going on a different track. And that track, when you put model on top of it, looks like it's metal enriched. And the simple explanation here is that this axis, this color shows CO2 absorption. This color shows carbon monoxide absorption. And things that form like planets are overall more metal rich, and they have more CO2 in their atmospheres. So this was kind of the tentative conclusion from this paper. What William has done then, they actually got a cycle 4 program to look at more of those systems. And sure enough, this is the new data that's not published yet. All these objects that were hypothesized as planets they're following the CO2-rich track. And we're hoping to start using these diagnostics, what I call reconnaissance, as part of just detecting an image before spending the tens of hours doing spectroscopy. You detect it, you do this color, and you kind of have a feel for how metal-rich a planet is from the get-go, before doing all the detailed modeling. So this is one of the nice things about this sample for this new program is these objects were actually first targeted based on prior informed measurements. So we know the dynamical masses, and we can play this game of correlating the metal steel planet atmosphere with the actual mass or with the mass ratio and see which formation pathways explain what's going on. All right, so the summary of reconnaissance with JWST, summary, it's more where are we doing next? There's about 1,000 stars within 100 parsecs are lower than 100 mega years, where we can do let's look at young stars and try to find sub-Jupiters and Saturns. JWST has already looked at 300 of them. So from a demographic standpoint, we'll just have the answer. We just have to wait for the result of these follow-up programs. We'll get an answer within 2 or 3 years. And maybe they will be very rare, or maybe there will be a lot of them, and we'll have a lot of work to do with spectroscopy. Now, there's 10 to the 3 stars of all ages within 20 parsecs. And those, we know the statistics from radial velocity, so we don't need to do blind surveys. But once you collect photons from a planet, you can do a lot of cool things with it. And that's what I'm going to show in the rest of my talk. And we won't have to go blind. We will have indirect measurements combining astrometry with radial velocity to know which system to look at, which one is interesting, and we're going to get into that. So oh, and one thing that's important here on this figure, this clicker is the thing. On this slide is distance matter. This is why the alpha sense system is so important. We have to confirm this candidate. It's so close that the kind of characterization you can do with something that's in our backyard is very unique. And that's why it's really important to confirm this candidate that Chaz and Aniket found that's disappeared because of its orbit. We really want to confirm it and being able then to do all the detailed stuff. So those detailed studies, I've alluded to it. It's, the end goal is spectroscopy, but I'm going to first talk about architectures before getting into spectroscopy. Because I think the context of the whole architecture is actually important when you try to get down to the formation mechanisms. So let's go back to the 14Hz system. So this one, there's this outer planet we're imaged with JWST. There's inner planet at 2, 3 AU. The other one is at about 13 AU. Their orbital planes are misaligned by about 30 degrees, if you believe the prograde solution. This was the key measurement we made with this, based on the RV and Hipparcos, based on RV and astrometry, the mutual inclination. We knew they were not completely orbiting in the same plane, but we weren't very sure exactly how misaligned they were. Once you get an imaging point, you can nail the orbital plane of one of the planets, and you can have a much better control of the mutual inclination. And both are moderately eccentric, so 0.3 and 0.5 eccentricities for the planets. So this is a dynamically interesting system. Then in the follow-up paper led by Tiger Lu, who was part of our team, he started running n-body simulations in the system. And the first question was, can this be explained by planet-planet scattering with just the two planets that are in the system? So he started throwing a bunch of simulation at it. And what you're seeing here is that if you're trying to reproduce a system with just two planets, after you propagate it for long enough, you just can't do it. The system with two survivors don't exist. The planets either collide or one of them gets scattered, but you can't find this orbital configuration just with two planets. If you invoke a third planet, a third lower mass planet that was in there at the beginning, that was formed with those three, and with those two, and then the orbits start crossing, and there's a chaotic zone here where one of the third planets gets ejected, then you can really reproduce the outcome in mutual inclination eccentricities for this system. And so, you have to invoke something a little bit dramatic, some catastrophic scattering to explain the system. And so then the question is this credible? Does it happen often, or is this kind of a unique case? We can actually probably get a much better answer to this question than what it seems. One of the first things we can do is really look at this system with the Roman coronagraph. This is what Clarissa has been doing. The inner planet for this system is actually very amenable to observations with Roman. Whether or not it's going to happen depends on a lot of work on the exposure times with Roman, and I'm not going to get into those details. But what's important here is when you look, going back to the California Planet first sample, when you look at this recent paper, there is a lot of systems. So these are the multis here. There is a lot of systems with inclination in the 0.3 to 0.5 regime. And there is a lot of multiple systems. And there's some of them, there's singles, but there's actually a trend, and you may have another companion there. This game, we played with 14 we should probably be able, if you really look at this sample very carefully, we should be able to play it for at least half a dozen systems and really get to a better understanding of whether or not this scattering scenario is ubiquitous or if it's a rare event. It's important because our solar system has 4 giant planets. It doesn't live in a system with only one giant planet. So having understanding of the multi-giant planet system form and evolve, and in the case of scattering, it's just evolution, is an important question to place our solar system. Now I'm going to leave JWST for 5 minutes. I'm going to keep talking about architectures. I am going to go to precision astrometry, and interferometry is back. So this is data from the VLTI gravity instrument. And what you are seeing here is it's an image with the gravity instrument. It's not an image. It's a bunch of fringe visibility as a function of wavelength. These are the raw fringe visibilities. That's what they look like. After you reduce them, this is what it looks like. These oscillations here, it means that the instrument has detected a planet. This is actually the Beta Pictoris B planet. And the tricks we're playing to go from here to here are the same for those who are doing high contrast imaging in the audience, the ADI, the spectral differential imaging. These are the same tricks we're doing. It's just using a different, more abstract object than just an image. You live in a different vector space, but this is all the same thing. And this has been extremely successful over the past 6 or 8 years. This is the first paper published by Matthias Novak on the Beta Pictoris spectrum. With this spectrum here, this was really the first time we had something exquisite from the ground where we could make inference about the metallicity of one of these young self-luminous planets. This is work by Jens here. where we first published with gravity the orbit of the other planet on the system. And there was something off once you really knew the orbit with gravity. Combining this orbit with the Gaia-Hipparcos accelerations, there was some mass missing. Like the star was moving too much. You could actually somewhat predict if there was an inner companion, what it would be, how massive it would be. Sasha Hinglik actually got a couple of nights of VLTI. They had to place this fiber and try different spots. But sure enough, they were able to detect the inner companion here that's at about like 12 Jupiter masses and measure its luminosity. There's a very nice, interesting story in terms of evolutionary track that goes with this object. And this is kind of what I was talking about earlier. There is no image of this planet. There is, there is a detection map in the fiber, and there are fringes. But this is still a direct detection. You're getting photons. You can measure a spectrum. You're resolving it from this. And there's a lot more planet detection that can be done with gravity. There's a lot of ongoing programs now going on in Europe trying to push for that. In the context of this talk, I'm mostly going to talk about the orbits you can do with gravity. This is work William was doing before they get sucked in by JWST. These are orbits of brown dwarf. This is the orbit of the A-flat-B planet. And what I want you to notice is the size of the uncertainties here. This is like sub-millisecond astrometry. And when you look at the comparison from like the regular coronagraph data, GPI sphere with what we're doing with VLTI without, making sub-panels, the error bars are minuscule. I mean, on this one, I think it's 100 micro-arcsecond uncertainty on the astromet. And so you can do very, very precise measurements of these visual orbits for these planets using an interferometer. What can you do with that? Well, those planets, again, they have orbits that are 50 or 100 years. So if you want to measure even an eccentricity, it gets hard, except if you have tiny, tiny error bars. Because then you can still measure the acceleration, get the acceleration vector, and kind of constrain what is happening here. This is something that Jason Wang realized early on in the gravity collaboration. And he started collecting these and building up these orbits for all these objects that we've looked at. So this is a sample, I think, of like 50 brown dwarfs and planets orbiting nearby stars, young nearby stars that have been measured with gravity. And Jason's student presented this result at the Spatially video, which is, I think, it's very interesting. The color coding, there's an arbitrary cut of 13 Jupiter masses. But you can see that this part here, the lower mass part, has lower eccentricity than the higher mass part. And Jonathan presented it as the planets, which just have a peak of eccentricity distribution near zero, where the brown dwarf have a very neat and distinct peak around 0.4 eccentricity. And that's, we think, is really a fossil tracer of formation and evolution of these objects. So how do we place this in context with the broader population? Going back to the RV sample, and a few months ago, Sarah Blunt published a paper showing that, so no, we're talking about planets outside of 10 AU. Now let's go inside of 5 AU and see what is the story in terms of eccentricity distribution. And the story is very different. For this time, the lower mass planets have no significant peak in eccentricity. But above 3 Jupiter masses, there is sort of an eccentricity pileup between centered about 0.3 eccentricity. So Sarah put out a bunch of hypotheses in her paper to explain what's going on with this. For instance, the more massive ones here could be the result of a disk instability formation. And then those are for microaccretion. When you compare those two results, this doesn't make sense. If this sample here was a result of disk instability, then we wouldn't have this pileup here past 10 AUs at zero eccentricity. Disk instability is even more efficient at past 10 AUs. So you put this together, and you can completely rule this. There are some stories about secular interactions by companion style effects, planet disk interactions. There's more theoretical work that needs to be done. The solution favored in Sarah's paper, again, was invoking more catastrophic event, planet planetary or or giant impacts. The scattering actually, we can actually test with JWST. This is a very clever idea. It's an ongoing program, and I'm going to give the kudos to Jens for coming up with this idea. By doing an actual blind survey of 30 stars in SCOSEM. So here's the story. Same thing. This is the Fulton 2019 distribution based on radial velocity for 1 to 15 Jupiter mass planets peaking at like 3.5 AU, and these are the GPI sphere survey, the ground-based elliptic survey, where there is nothing. It turns out if you comb over the literature, there is an abundance of things in SCOSEM, so 5 to 15 megayears. There's just a lot of wide companions that have been found. A lot more than in older moving groups like Beta Pictoris and so on. So what could explain this? Well, the simple explanation is to say it's just gravitational instability. These stars are young, so the planets of Brandorf's a little brighter, and so we're able to see them. The other explanation is to say, well, these are actually planets that are actually being scattered. And at this age, we're seeing the scattering happening we're seeing the scattering happening sort of in front of us. And there's a very simple way to test it, is to go to a sample of lower mass planets, so 0.1 to 1 Jupiter mass planets. And JWST lets us do that. We can really easily test if there are planets around these 30 stars that are down to 0.1 Jupiter masses. This is we're talking about things that are past like 100 AU. Technically, it's very easy to do. And this is a nice figure that Jens put together. You know, if GI can explain this, we won't find anything. If it's really these are core accretion planets that are being scattered, we'll find 3 or 4 companions. So these are all our candidates. This is the same game. This work done by our postdoc, Laurent Pueyo. These are all candidates that are in blue here, the background stars, and then the extragalactic population. These candidates here are promising. We're not able to get our ducks in order before the cycle 5 deadline to follow up these objects. We're hoping to follow them up in next cycles. But I think we're getting to the point for this sample to kind of, at this age of 5 to 10 megayears, 5 to 15 megayears, to get an answer about whether or not scattering is ubiquitous or it's kind of one-off kind of thing. All right, so are catastrophic and ubiquitous? And if they are not, really following up the RV systems, we're going to have beautiful architecture informations about how these planets orbit each other. We can go back to the dynamical history, and we're going to have a lot of context once you get to the actual composition of the planets, once you start doing spectroscopic observation. And that's the last part of my talk. That's the deep dive of spectroscopy. So this is what the picture was before JWST. This is with gravity again, paper by Jens. So this is kind of the same objects that I showed you earlier for eccentricities, or the K-band spectra that are going with gravity. Most of what we could do is looking at this transition between CO here and methane here. Once you go from hotter exoplanets on Brandorf to cooler one. And the emerging story, when you look at just CO and methane, is that in low gravity objects, in young planets, there's more vigorous vertical mixing. And it triggers the onset of like the CO4 rich, CH4 rich atmosphere is triggered at lower temperature. And sort of what you're seeing here with this young planet sequence that crosses over lower than where the Brandorf crossover. And this was kind of tentative. This was the data we had, and this is the best we could do. Now let's just look at one of my favorite objects, which is the first blob I found in speckles using Palomar. I'm very fond of this object. It's a 50 Jupiter mass Brandorf orbiting a nearby sun-like star. This is the JWST NIRSpec data. This is the raw data. This is after you push it through Jean-Baptiste Ruffiot cross-correlation pipeline. And sure enough, there is a big 100 sigma detection of this point source here. What you can do with the spectrum here, and this is a follow-up paper published by Kill and Hawk here, is this is in black, it's the data. It's actually the error bars are tiny. This is a very high signal detection. And you get the JWST 3 to 5 micron spectrum. And what we're doing here is we're fitting model grids And so here you have your water. Your water is here. This is methane. This is CO2. This is CO. They're all detected. But the relative abundances, it's a mess. None of the 4 models can actually match that. And then we asked Travis Barman to say, OK, can you make a custom model for us? And the only thing Travis changed was the vertical mixing. So dredging up CO, bringing it higher up in the atmosphere, and doing it self-consistently with the chemistry. And you do that, you tune your KZZ, and sure enough, it fits the data beautifully. This part, the water, let's forget about it. We don't believe it. I think there's something wrong in the data. But as far as the carbon is concerned, so CO, CO2, and CH4, the story is very nice and consistent. This is an interesting result in Cell that Killen published. But that's, we went from this vague, yeah, maybe mixing does something in low gravity atmosphere story that we had with our ground-based data to this very precise inference we can make on very high quality data. And that's where our field is completely switching. We're making this switch as we go. This is 2 years, 2 or 3 years, 3 years old now. It's very recent, and it's taking a lot of us doing direct imaging, a change in mindset to live in a part of the world where the data is actually looking so good. Now, Jean-Baptiste and Jerry, I've made this switch. This is the beautiful spectra of the HRD 79 planets, where you're detecting CO2, isotopologues of CO, and they're even detecting H2S. So they're detecting refractory elements, things that can only come from the solids when you form the core of the planet. They come from solids. They can't come from gas. And that gives us important clues about the planet formation. Because this system, HRD 79 system, has 4 planets, you can start playing the game of what is the relative composition with respect to position in the protoplanetary disk and primordial disk. One really cool result in this recent paper by Jerry is the detection of nitrogen in the outer planet right inside of the snow line 4 and 2, which is a consistent picture with how what's happening in the disk. And what we're starting to do is a molecular inventory of the species as a function of the formation location in the disk. Thinking back about the dynamical story I was telling you earlier about scattering and migrations, this is going to be a different way to test that once all is said and done. This measurement is actually, so this was the second time this technique was applied to JWST NIRSpec data. It's becoming routine. Emily Rickman is PIing a program looking at about 10 or 12 brown dwarf companions. They're all detected. Even the things are pretty close to the star, like 150, 200 milliarcsecond. I mean, this is like 2 NIRSpec spaxels. If you do cross correlation, you lose the continuum, but you're able to detect them and get all these molecular detections. It's going to give us some insight about the vectoral structure for brown dwarfs. There's a lot of detailed atmospheric physics. Brown dwarf detailed atmospheric physics you can do with those. And in terms of molecular abundances, we know those things didn't form like planets, but this is the control sample for the planet population. And the reason we started with this proposal is we sort of knew those observations would be easier than if we went after like bona fide, like radial velocity planets. It turns out that I am surprised by how well this is working. I wasn't expecting having just a regular tool that just crunches the data to produce such high quality data. The previous result I showed you was really Jean-Baptiste, spending a month trying to fine-tune stuff. Once you do a survey, you don't have a month to fine-tune stuff. So, but it's working really well. And so Alex Madurovitz is actually leading the reduction for this, and Alex started thinking about assembling a sample of now directly images or RV planets, and there are actually some RV planets in this target list here that lay in a place where you can actually, if they're outside, far away enough from the star, you can actually straight up do NIRSpec spectroscopy and try testing try measuring the molecular abundances in their atmospheres. And that's something that I think no JWST observations are planned to do that. But I think the field is going to grow, and we're going to be trying to do a lot more of this over the next 3 or 4 years. I mean, it's to go through a TAC. There's a process, but these things have a way to work out where the best science always comes out. And one thing that I'm particularly interested in is really comparing these two populations at different eccentricities, and maybe we can actually get some clue in being able to correlate something in the atmospheric abundances with the dynamics. This is kind of maybe a pipe dream, but at least we can ask the questions now, and we know we can get the data to answer those questions. Whether or not the answer will be conclusive is a different story. But it's remarkable that we can actually ask those questions and try to go. Now, eventually, as I was saying earlier, the planets get too cold. So observing them from 3 to 5 microns, it doesn't work. You have to go to 10 microns and use the MIRI instrument. And this is this planet here, the JWST B planet that was discovered by Anne-Marie Lagrange a couple of years ago. This planet is quite interesting because it appears that it's exciting Trojan resonance in the dust belt around the star. This disk has been known for about 10 years. And the asymmetries in this were known, but Anne-Marie was able with the MIRI instrument to actually see the planet. And this planet lays in a very nice space, part of the parameter space. It's cold, it's 300 Kelvin, and it's very young. What can you do if you get a spectrum of such a planet? And this is a recent paper by Christian Wilkinson. So what Christian is a theorist, and Christian was trying to do self-consistent models where you tie together the interior model with the atmospheric model. And there's been several attempts to do that. And the name of the game there is to eventually get to the core mass. And if you want to get to the formation history, you want to measure the core mass of the planet. And I really like this figure here. What the key uncertainty here is the stitching point between the interior model and the atmospheric model. And if you look at your favorite hot or warm Jupiter, because they're irradiated, that point here is at about 10 to the 4 bars. The data is not going to get you there. You're going to measure this with your spectrum, and then you're going to hopefully done the interpolation stuff consistently, and maybe you'll get a result for a core mass that's plausible. For a young, low-gravity, cool temperature planet, which is JWST-B, the stitching point here is actually at pressures that you may be able to observe with a MIRI spectrum. And this is the point that Mathilde, Malin, and Christian made in their proposal, where you may be able to measure a core mass based on this MIRI spectrum of this planet here. So these are observations that are planned for next year. And we may be able to finally, for these cooler objects, cooler and younger objects, tie together some idea about what's happening in the interior model. We're not going to measure a fuzzy core. We're still going to the astrophysics way. We don't have the detail of the Juno mission. But we may be able to get a big sample to try to understand our solar system in context. Now, there is a big caveat in this proposal. As you go longer in wavelength, things get really ugly from the data side. So I'm going to show you a deep dive on the MIRI data. You have a lot of word effects with MIRI that don't exist with NIRSpec. First, the background goes higher. Even if the Corot telescope is JWST, the background is going to go higher. So you're going to have to fight background. But it's probably not going to be so bad. It's going to start getting bad at like 12, 13 microns. Below that, it's going to be. You have this trail light effect. There's this zipper effect on MIRI that we can sort of empirically model. We don't really understand where it's coming from. This is the detector is actually a beautiful Fabry-Perot interferometer that's creating fringes on your data in your data. Now the name of the game is to look at these absorption lines for molecules, and sure enough, this looks like an array of lines. So if you're into cross-correlate with the molecular template, you're going to fit your Fabry-Perot fringes from your interferometer. So this needs to be calibrated. Alexis Bido in our group, who doesn't have a picture of himself on the internet, so I couldn't put a picture of him, he's the only one, actually really started working hard on this about a year ago. And he's done a fabulous job. This is what you get on the HRA79 system with the regular JWST pipeline. This is what you get from Alexis' pipeline after you're fitting the fringes and the zipper and all the other effects. You can get much, much higher SNR. And based on this result, the TW7 experiment that I showed you earlier, you should be able to see that planet with high SNR. What's even reassuring is, so these are the HRA79 planets. Anthony Bocalotti's data is writing a paper on the science, but one quick check that Alexi and Jerry actually did. Alexi took Jerry best fit spectrum from the NIRSpec data and compared it to the MIRI data, and they agree very well. So there's nothing crazy happening. So the future is really great for exoplanet spectroscopy with MIRI. This is something that's just starting this cycle, but that's something that I think is going to grow. So I'm almost done. Some eye candy here. When you go to younger wavelengths, you can do amazing things. This is the WSCS system, a nature paper by Killen, where in the same system, she detected a circumplanetary disk, the access from a circumplanetary disk, and silicate clouds here. What you see here is a silicate feature in the atmosphere of the other planet, of the outer planets. There's a whole story about this exoplanet atmosphere that goes with clouds. I didn't have time to go over it. But this is the kind of science you can do once you go to longer wavelengths. Mathilde published the spectrum of 13 Jupiter mass companion to 2 M stars. The whole point here is the spectrum is flat. It's not supposed to be flat. It's supposed to be going down. There's a high infrared excess. This is a carbon-rich disk. We have H2 winds that are coming out of the disk. They're marginally spatially resolved. You can think of it as a scaled-down T-Tauri star. Like the inner source for the T-Tauri star is something that's 10 Jupiter masses. But the same diagnostics, accretion lines, variability in the accretion lines, they're showing up in these objects. This started as a 2-hour experiment. This was just only 2 hours of exposure with some leftover guaranteed time observations. There's about 150 hours of time dedicated to these objects, not these other objects. Brent Bowler out of Santa Barbara is really leading this, pushing this effort. And a lot of amazing stuff is going to happen on this field here. I like to call those, I mean, the official term is circumplanetary disk. I like to call them moon-forming disk. It has a better sound to it. But this is sort of what it is. This is dust around something that probably formed like a planet. So what I'm most excited about, the coronagraph imaging will answer once for all if Saturn's past 10 AUs exist, we're going to get the answer. The moon-forming disks are getting me very excited, even if this was just my last slide. I think there's a lot of growth to it that's going to happen. And really, the core of my talk is really, we want to connect measurements of giant exoplanet architectures and composition, put all of them together for the planets that are cool enough. We might go a little bit beyond just the atmosphere, and we might understand something about the interior structure, or at least the core mass. And if we can do that by sufficiently large sample, I'm thinking like 12, 2 dozen. We'll be able to place our solar system in a much better context than where we are when it comes to giant planets in our solar system. The other thing I'm very excited about, for those who know me, my background is in instrumentation data analysis. Machine learning inspired methods are completely taking off this year. This is Louis Dedois revisiting the JWST MIRI data and kind of improving the sensitivity by an order of magnitude. This is the same thing done on coronagraph data by Rodrigo Ferrer-Chavez that he presented at the Spiritual VR conference. This is going to really change the way we look at the data. So the thing I'm a little less excited about is we're going to have to do it over again once we figure out how these new methods work. All I've shown you throughout this talk, these are data analysis methods that are 10 to 20 years old. And I can tell you that all the data I've shown you were about a factor of 5 or 10 away from the fundamental statistical norms. So if you use better data analysis, we're going to be able to calibrate the systematics, and we're going to be able to go deeper to anything I've shown you so far. And I'm probably going to look at the younger generation doing that work and try to enjoy it. Thank you so much. These are the eye candy pictures of the systems, and I'm done. Thank you. Yeah.
Here.
Uh-huh. Uh-huh. So there is one caveat that I didn't get into. It will be solved over the years, but all the spectra I'm showing here, they're flat. And there's a good reason. What we're doing is cross-correlating with templates. So we're losing the continuum. So we cannot do this measurement that you're talking about. Now, doing this measurement, retrieving the full continuum, for this object that's bright enough, we're able to do it. It's being able, it's in the data. We have to treat the data in a different way. We have to be a little more clever about data analysis. One of the things, and I think the answer is in ML-inspired methods. Once we get past that hump, we're going to do this measurement. And that's one of the things I'm really excited about. Having this 2 to 15 microns SED, we will get the bolometric luminosity. And this problem we've had in direct imaging about the radii being completely wrong all the time. I mean, as you know, if you're a friend of William spent a year on the FLET paper fighting with the radius, and we just gave up. We said, OK, well, we don't know what it is, and it's fine. We're writing a paper anyway. We'll be able to measure it. I think this is going to happen. But because the way we're analyzing our data right now, we can do it. Yes. That's a big question mark. As I mean, precision will be helpful on the actual measurement of the interior or on the data. No, on the I mean, if you believe this model here, where I do believe the data and the level of precision in the data because it's consistent with all the work we've been doing. You know, we're getting to core masses of like 30 Earth masses plus minus 10. That's still pretty broad. The part that I'm less comfortable saying this is absolutely right, it's more what's happening inside of the model, because I don't model planet interiors for a living. But this is what we're expecting from this. No, we haven't seen that yet now. And I know for the gravity sample, they've looked at all the possible correlation to see if there was anything, and we haven't. Well, parts of it is it's because like that sample, the gravity data, it's in K-band, so we don't go below anything like 700 Kelvin. So, and the coolest one is 51 area, and it's really hard to get. And so we're sort of in the same temperature regime. Like my suspicion is we're able to look at that from 300 all the way to 1500 for those young planets. Now we have enough level arm in temperature to ask questions. Right now, I think our sample is just too biased towards the other ones, and they're sort of all the same. Hey, Chaz. Yeah. Yes. I mean, there are. I mean, you're talking about like orbital scales of like 3-5 AUs, like solar system scales. But they're in total 15 parsecs. I mean, if I think for those, JW is probably going to be able to see that. I mean, there's a bunch of programs now. The big issue, I mean, there's Kyle Franson as a program trying to do exactly that. And you know, you're choosing among your nearest stars. You're choosing based on like 2 vectors, Gaia, Hipparcos, and there's a big error bar. As you know, there's a group in France, American group is trying to do this, play this game. once we have DR4 and we exactly know what's happening, I think the problem is more selecting the right targets right now. And because everything is degenerate, half of them are stellar binaries. Well, that's just a binary. But once we know where to go, there will be enough stars or close enough so we can do the experiment and go with GW. Talk to me in 5 years, but I'm pretty optimistic right now. Yeah, MIRI. And no matter, let's try to get as close as possible in symmetric access with MIRI. Now, there is one technical problem, which is bright fatter with MIRI that we need to solve. William had a program we think we've detected the planet, but bright fatter is giving us a really hard time. With MIRI, you have a lot more technical problems, and we need to fix them before we can do the things that I talk about with MIRI. No, so by moon forming disk, I'm saying it's a disk around a Jupiter or super Jupiter. Whether it's forming a moon, we don't know. But there is gas, there's dust, there's stuff happening. So there are two angles. The real angle there is you take this data to people that do T-Tauri stars and accretion and they are you tell them, try to help us interpret the data. And they're like, whoa, this is too low mass. We're going to have to retune our models. Like, it's really opening up a new theoretical avenue, where a new sandbox for theorists to play, and thinking about this type of protoplanetary disks, but not protoplanetary because the source is more of a planet. So that's why it's exciting, because it's opening a new area. The data is coming because people get excited about it. The moon angle for this specific object, most of those are young, 1, 2, 3 mega years. This one is 50 mega years, which is a big puzzle. How can something that's 50 mega years still create? And so then the jump is like, oh, there must be a moon. Whether or not there's a moon, I don't know. But this one is a particular puzzle because it's that old. I mean, relatively to the age of a typical T-Tauri. Yeah. Yeah, so that you would have to look at Jonathan. Jonathan has figures on that. You have to look at Jonathan's paper when it comes out. There is a lot of that discussion in his paper. I try to stick to what he presented publicly as Spirit of Leo, not to steal his thunder. There's discussion on that.
So you spend more than a decade preparing.
The biggest surprise to me is that everything is working. No, no, the biggest surprise is, I mean, there are technical surprises, but the thing I did not appreciate, I mean, during that decade, I was preparing for JWST and working on very fancy adaptive optics system from the ground, where the actual contrast for this system is much better than JWST. In terms of killing the star, JWST is not that good. And the part that really did not appreciate is what going to the infrared buys you. It buys you so much more science. And the star starts going down, so the contrast is fine. And it's not a fundamental surprise. I should have known this, but it's still, every day I'm like, oh, wow, that's because we're at 4 microns. We couldn't do it at 2 microns. And I think I'm reminded of this every few months. And the fact that everything worked is also a big surprise. There were question marks. MIRI is a very, very complex instrument. And the fact that MIRI is delivering what it's delivering now is remarkable.
Thank Laurent again. Run it for 1